Welcome and thank you for enrolling in our online course. In this initial lecture, you will be provided with a concise introduction to pacemaker battery technology. Let's begin with Ohm's law. Ohm's law is a critical element in understanding the relationship between device functionality and current flow. It states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. By introducing the constant of proportionality, the resistance, one arrives at the usual mathematical equations that describe this relationship. I equals V over R. I is the current through the conductor in units of amperes. V is the voltage measured across the conductor in units of volts. R is the resistance of the conductor in units of ohms. More specifically, Ohm's law states that the R of this relationship is constant and independent of the current. Ohm's law can be expressed in three ways, as represented in the triangle. The line that divides the left and right sections indicates multiplication, and the divider between the top and bottom sections indicates division. When solving for the voltage, expressed in volts, use V equals I multiplied by R. When solving for the current, expressed in amps, use the equation I equals V divided by R. When solving the resistance, expressed in ohms, use R equals V divided by I. By using this triangle, let's see an example. If the voltage is 6 volts, and the resistance is 500 ohms. What is the current in amps? Simply, use the formula, I equals V divided by R, so divide the voltage by the resistance. In this case, 5 divided by 500, is equal to 0.012 amps, or 12 milliamps. When considering the application of Ohm's law in an implantable device, and thinking about resistance to the current flow in the pacing circuit, one must be aware of the factors that create resistance within the system, which include lead resistance, tissue impedance, its capacity properties, and polarization resistance. Current is measured in amps and expressed in milliamps. Normal pacing impedance sits at 500 ohms, and impedances greater than 2000 ohms indicate a lead fracture. The power is measured in watts, and it is a measure of the rate at which energy is delivered over time. 1 watt is equal to 1 joule per second. Power can be expressed in Ohm's law by rearranging its components. When using voltage and resistance, power equals V power 2 divided by R. When using current and voltage, power equals I times V. When using resistance and the current, power equals R times I2. For example, if the voltage is 3 volts, and the resistance is 500 ohms, what is the power in watts? Simply use the formula. P equals V power 2 divided by R square the voltage, and divide that by the resistance. Say 3 volts, over 500 ohms is equal to 0.018 watts. Energy is measured in joules, and is formed by multiplying power by the time the power is delivered. E equals P times T. Energy is most frequently used as a way to measure the defibrillation output of ICDs, as in 40 joules of delivered energy, or in an external defibrillation of 200 joules. Next, we are going to see the basic circuit component of the pacemaker battery. The basic circuit components of cardiac implantable electronic devices are resistors, capacitors, transistor, diodes, rectifiers, CMOS, transformers. Let's take a close look at a resistor. The pacemaker circuit may include a resistor connected in series. The resistor will resist or slow the flow of electrical charge. The conventional unit of measurement is ohms. All electrical circuits, including pacing and defibrillation leads, have resistance. Resistance is used interchangeably with impedance when discussing pacing and defibrillation. Here is the formula for calculating the resistance. In a series circuit, the current through each of the components is the same, and the voltage across the circuit is the sum of voltage across each component. In a parallel circuit, the voltage across each of the components is the same, and the total current is the sum of the current through each component. Our next component is the capacitor. It stores and discharges the electrical charge. The unit of capacitance is the farad. It is used in the pacing circuit to store and deliver the pacing pulse and it is used in the defibrillation circuit to store and deliver the defibrillation pulse. The modern transvenous ICD circuit capacitors are 100 to 160 microfarads. The formula for calculating capacitance is C equals Q divided V, where Q is the charge of the conductor, V is the potential of playing across the conductor, and C is a proportionally constant called capacitance. Another basic circuit component is the transistor. It is an electrical switch within a circuit. Transistors function as current regulators by allowing a small current to control a large current. Billions of individual transistors are built into the circuitry of the pulse generator. The next component in our basic circuitry is the diode. The diode allows electrical current to flow only in one direction. The name of the diode, commonly used in pacemaker circuits, is Zener. Zener diodes protect the pulse-generated circuit from high external voltage, for example, during external defibrillation. The rectifier converts biphasic signals to a signal with only positive components, as shown in the graphic. A half-wave rectifier only outputs the positive portion of the signal, and a full-wave rectifier converts the negative portion of the signal into a positive signal. Half-wave and full-wave rectifiers are used in pulse generator sensing circuits. The complementary metal oxide semiconductor, or CMOS, can be found as elements of microprocessors and electronic circuitry of the components found in the pulse generator. It is most susceptible to radiation. The last in our list of basic circuit components is the transformer. It converts an input electrical flow to an output electrical flow of higher voltage and lower current. It is used in defibrillators to charge a capacitor to 900 volts from a 300-volt battery, and in pacemakers to create a pulse output of up to 7.5 volts from a 3-volt battery. Let's move forward with battery technology. Here are two examples of early battery technology. One is a nickel-cadmium battery, and the other one is plutonium batteries. Another example of early battery technology is the mercury oxide zinc battery, which has a very flat discharge curve, and the delivered 1.3 volt cell voltage. A small amount of hydrogen gas is created in reaction by the product, so it needs venting in the generator shell, and this is more prone to fluid infiltration. This table shows the difference in the cell voltage of current battery technology. Cell voltage determines the battery's ability to generate pulse energy and charge the defibrillator. The battery with lithium iodine has 2.8 volts of cell voltage. A battery with lithium manganese dioxide has 3.3 volts of cell voltage. The battery with lithium carbon monofluoride has 3.1 volts of cell voltage. A battery with lithium silver vanadium oxide, commonly found in ICDs, has 3.2 volts of cell voltage. Let's deep dive into the basic functions and electrochemistry of batteries. A battery converts chemical energy into electrical energy. The source of this energy is electrochemical reactions that occur within the battery. The type and amount of material participating in this reaction determine the deliverable energy of a battery. It's time to focus on battery technology. The major parts of a battery are the anode, the cathode, and the electrolyte. The anode and cathode must be physically separated, and both must be in contact with the electrolyte. The two battery components involved in the electrochemical reaction during discharge are the anode and the cathode. The anode, usually lithium in most medical batteries, furnishes electrons for the external circuit, whereas the cathode, usually an oxide or halogen-rich compound, receives the electrons. The anode is defined as the electrode, at which electrochemical oxidation occurs, and the cathode as the electrode, at which electrochemical reduction occurs. This schematic diagram is the representation of a sealed battery. The anode material is on the left, the cathode material is on the right, and the electrolyte is in the middle of the cell. The discharge reaction is A plus C equals to AC. In this example, both A plus and C minus are mobile ions, and the discharge product AC is insoluble and precipitates in the electrolyte solutions. The lithium silver vanadium oxide battery is used in the majority of ICDs today. It is optimized for pulses of high current to charge the defibrillation capacitor, quickly known as high-rate batteries. The desirable characteristics of battery technology include high energy density, low self-discharge, small size, a highly predictable discharge curve, and solid-state chemistry. The image on the right shows an early pacing circuit, designed by Elmquist. Longevity is typically defined as the interval between device implantation and the detection of an end-of-service indicator. Because therapy can vary substantially from patient to patient, the longevity requirement is typically linked to a specified set of nominal conditions and programmed parameters. The minimum battery capacity required to achieve the specified longevity can be calculated from the average current needed for this nominal set of conditions. The battery capacity is measured in the unit of amp-hours. If a battery has 1 amp-hour capacity and the circuit drains 0.5 amps per hour, the battery would last 2 hours. If the circuit drained 1 amp per hour, the battery would last 1 hour. The battery used in pacemakers ranges from 0.4 to 1.5 amp-hours. The current drain is measured in microamps. The relationship between battery capacity and current dryness is that 1 amp is equal to 1000 milliamps, whereas 1 milliamp is equal to 1000 microamps. 1 amp-hour battery has 1 million microamps of available capacity. When the pacemaker output stimulus is not delivered, the pacemaker drains an average of less than 10 microamps of current per hour. These 10 microamps are used to run the circuit, while the pacemaker is inhibited. Next, we move on to the factors that affect current drains, which includes pulse amplitude, pulse width, pacing rate, pacing mode, percentage of pacing, and lead resistance. When the pulse amplitude and pulse width are increased, the current drain is also increased. When a pacing mode is changed from one to another, the current drain also changes. When the pacing percentage is increased, the battery longevity is also reduced.
You've just completed another vital step in understanding cardiac pacing. Let's keep the momentum going. We'll be exploring more essential topics in rhythm management devices in the upcoming videos. And now it's your turn to check your progress. Head over to our website where we've built 2 assessment tools just for you. A knowledge assessment with 500 plus MCQs from the entire Beginner's Guide series. An IBHRE style exam simulation consists of 5 blocks, 40 questions on each block, timed to help you sharpen your time management for the real exam. Whether you're studying for IBHRE, CCI, IBHRE, or simply want to sharpen your clinical understanding, these assessments are your next step. Click the link in the description to get started now. If you're enjoying this series, like, share, and subscribe to Medfoxes. It really helps us grow and reach more learners. Thanks for watching, and I'll see you in the next one.